So in this video, guys, we're going to be talking about the concept of a derivative. But even before that, we're going to be explaining what the concept of a derivative is. And we're going to be expressing that in terms of a tangent line. Let's just try to draw a curve that's simpler to observe. So basically, we have a point here. Let's call that point A. And we know that the function would represent f of a over here. This might not be very relevant, but still it's good to understand that if we have a function f over here, the particular values are going to be given by a and f of a and b and f of b, right? So in the previous video we discussed how we're trying to find the gradient of the secant line, right, which is basically the dotted line from this point to that, and that represents the average rate of change. But what if we want to go beyond that? And think about this, guys. What if we want to find the average rate of change, or not just the average rate of change, the rate of change at a particular point, and see how the function behaves when we get very close to a particular point? So what I'm going to do is I'm just going to erase this, and I'm going to be representing a particular notation over here. I'm going to be trying to represent this point as the point at which I'm trying to determine the rate of change, right? The instantaneous rate of change, which is clearly written over here, right? So I'm going to try to get as close as I can to this particular point over here and move from that part of the curve over here, but get very close, very close to this point, but not exactly equal to it. And why is that? Assume that you're at a point over here and you're trying to get closer and closer to this point. Let's zoom into this and try to draw this over here. So what I'm basically saying is, this is the zoomed in version. This is a, f of a, and that's kind of the point that I've crossed out, right? Let's call that x over here, and that's x2. So I've kind of zoomed in over here, and if you take a look at it, and if you draw the secant line from this point to that point, you're going to observe something. You're going to observe a gradient. We all know that, right? And it's going to be very special if we talk about a point that's even closer than x. What if I try to get as close as I can to this particular point, but it's ahead of x? What if I'm over here? What if I'm over here? What happens then? Well, let's try to draw secant lines and see what happens. If I draw a secant line, and this is probably going to be a little rough, but I'm going to try to make this as neat as I can. So the gradient of this secant line is over here, and the gradient of that secant line turns out to be over here. If you think about it, that's the point on the curve. So what you're getting is three lines. That's one line. You have one secant line that's very close to this, right? But it's not exactly close to it. Then you have another secant line that's very close to the curve, but not exactly closer than the next value, which is almost exactly on the curve, right? So what do you see over here? If you think about it for a second, it's very obvious, right? We're trying to get as close as we can to the point a and f of a, and as we do that, the gradient of the secant line gets closer and closer to the gradient at the point a and a point close to that. So what I'm saying is, we've talked about limits in so much detail. At this point, we must be able to use that concept to our advantage. To be able to move an arbitrary point that could be called x closer and closer to a, make it approach very close to a, so that we can get something. So that we can perhaps get the instantaneous rate of change at this point and see what happens when x gets very close to a, right? So let's try to write that in a notation that's going to help us. But even before writing out the notation, I want you guys to understand something. This could be interpreted as something slightly different, but we're going to talk about that. So over here, I'm going to represent the point x, right? And it doesn't matter what f of x is, but let's just write it out for fun. We know that this is a point. I'm going to call this x plus h. And h is a very small number. So that kind of represents x plus delta x, if you think about it. But I don't want to deal with delta at this point. And this function value turns out to be h. So if you think about it, we're trying to get closer and closer as we move towards this side of the curve, right? What if I were to take the limit as h, the distance between x and x plus h? If you think about it, this is the distance h, right? If you think about it for 1 second, because that's like x and that's x plus h. I want the distance h to approach 0, get so small that I get another point over here, so I can draw a secant line that gives me a very good value for the rate of change at that point, or the instantaneous rate. So if I take the limit as h approaches 0 for f of x plus h, because that's a y value, right? If you think about it, and we have f of x over here because we were trying to subtract, because this is basically delta y if you think about it, delta y divided by delta x, and because that's f of xy and that's f of x, so if we subtract this we're going to get this, and if we subtract x plus h minus x, what do you think we'll get? X plus h minus x is simply going to give us h. So what is that going to give us? That's going to give us h. So h is approaching 0. This is a very good definition. Actually, this is helping us find the derivative at the point x. So think about it intuitively for a second. What's happening? We have a function value f of x plus h right over here, and we have a point x plus h, which is a distance of h away from this point. We're trying to find the gradient at this point, but that's not really the point. The point is we're trying to get closer and closer towards this point so that our approximation of the gradient gets better, so that we can estimate the gradient at this point. It's kind of irrelevant, not exactly irrelevant, but kind of important to mention over here that the gradient at a point of a curve is given by the tangent at that point, right? We all know that. So we're going to be using that concept over here as well. So if we try to determine that, what do you think happens as we get closer and closer to x? What happens is the gradient of the secant line basically between 2 points, gets very close, gets so close to the gradient of the tangent line at that point that it equals it. So essentially what I'm saying is that the derivative at the point x for f dash x has to be equal to this limit, because this limit tells us that the distance between x and x plus h is so small, and at the same time the distance between f of x plus h minus f of x is getting smaller and smaller, so that we're getting a line that's so close to x that it gives us the derivative, or the rate of change, instantaneous in other words. So this, guys, is the definition of a derivative. It defines the gradient at a particular point, but I won't use the word gradient, I'd use the word rate of change, because the gradient can be interpreted as the gradient of a secant line as well, and I don't really want to do that at this point. There are different interpretations of this as well. There are different ways of representing what this formula is basically. So I'm gonna just write it down once more so that you guys don't get confused. So we know that the derivative at the point x is given by the limit as h approaches 0 for f of x plus h minus f of x divided by h. That's something that's very important. We could replace this with an alternate definition which is not very different from this, right? So if you're trying to determine the gradient, or basically the derivative at a point x, we could rewrite this as f d by dx, right? Because we have a function over here, but I don't really want to call this a function. I want to represent this by saying that I'm taking the derivative of the point p, right? And once I do that, I get f dash p. We all know that, right? Function f ke andar basically we try to differentiate it and then plug in the point p. That's exactly what we do to find the derivative at a point. We know that for a fact. And this has to be equal to what exactly? This has to be equal to q trying to approach p, right? And q is basically an arbitrary point, and f of q minus f of p gets divided by q minus p. So there's not a lot of difference between this and that. Q is being represented by x over here, and that's the arbitrary value, right? And q is getting closer and closer to p, and p is the point at which I'm trying to determine the gradient or the derivative, and q is getting closer and closer to p, and f of q is getting closer and closer to f of p. So that is another definition of the gradient or the derivative basically. So the idea is I prefer using this definition because it makes proofs simpler, but you're free to use this definition as well. And that's just coming from my personal experience, because there are going to be certain examples which will require us to basically formally prove whether a derivative exists at a point or not. So we'll probably be doing some examples regarding that. So see you guys in the next video.